Hamiltonians are going to take your system, right? Like, and I'm going to either shift the position of your system or going to shift the momentum of your system, right? Depending on whether something rolls down a slope or if you give it a kick. These kind of operations are captured actually by what I now call classical displacement operator. The classical displacement operator simply takes a point of the space, puts it somewhere else. Yeah. So you can do this for along the momentum axis, along the position axis, and in classical mechanics, these things simply commute. And it doesn't really matter if you displace the momentum first or displace the position first. Okay, so this is classical mechanics. You all know this. So now when we go to quantum mechanics, we quantize, right? Like we take our position, momentum variables, and we lift them to be operators on some Hilbert space. We take our Poisson bracket that basically tells us whether or not things evolve onto one another into a commutator between these operators, and all our little phase-space functions get heads onto it, which means that they get lifted to be operators that act on a Hilbert space. So in quantum mechanics, the displacement operators become a little bit more meaningful. Now they're not just operators that displace things, either momentum or position, but they start to fail to commute. And this is an important aspect of quantum mechanics, which means that if I take a particle, I change its position, and then I change its momentum, the outcome state is by phase offset different from the state that you obtain if you did this operation in reverse. Yeah. So this is captured by this commutation relationship just up there. And this commutation relationship is the so-called Weyl form of the canonical commutation relations. It's very meaningful because basically there's a Stone von Neumann theorem that tells you that if you have two one-parameter groups of operators that commute in this way, then they're all equivalent, right? Like so which means that, which translates into the idea that, okay, all different ways to formulate quantum mechanics are unitarily equivalent. Yeah, so this is just to highlight the importance of displacement operators just in the basic formulation of quantum mechanics. So we know that they're important, we want to think about them. And we can also think about, okay, these things don't commute. Maybe there's a part of the quantized displacement operators that stay at the classical behavior, right? And those will be exactly those displacement operators where this phase vanishes. And this phase vanishing means that whatever is up there is product u times v. If that's an integer multiple of 2 pi, then the corresponding subsets of displacement operators commute. So this is going to be the first part of the story, in that you can think of GKP codes, which we will talk more about later, but when you come back, you'll notice this. You can think of GKP codes as the thing that stays classical when you quantize. Yeah, so I found this was a funny perspective. You can fiddle around more with like different ways to quantize manifolds and think about, try to learn about geometric quantization and try to make this a little bit more concrete. Yeah, I just thought this was a funny point. The whole key of this brief intro is to highlight that displacement operators are important. Okay, so let's think a little bit more about displacement operators. When we write down a quantum operation that implements a displacement operator, okay, like we know in quantum mechanics, we have a projective Hilbert space. Everything's up to some factors. So I'm going to write down a unitary transformation that implements a displacement operator labeled by these two indices. One of the indices labels a shift in position, and the other one a shift in momentum. And you also multiply it by some phase. Right? Like if you're projective Hilbert space, this phase drops out, but as a unitary operator, it can exist. And so the way to capture this unitary set of displacement operators is really just, I mean, this is written in an overly complicated way. It's just saying, okay, hey, I have this one vector that tells you where to go in phase space, and I have this extra label, this phase label here that tells you, okay, whether or not you multiply some global phase to your state. And the whole gist of these operators, as already seen in the previous page, is that they commute up to a phase where this phase now is dictated by the symplectic inner product between these two vectors by which you have to replace. Okay, so displacement operators are operators that commute up to a phase, where the phase comes from the label of the individual operators. In discrete quantum mechanics, we have operators that we care about very much, which behave very similarly. So if you think about qubit systems or qudit systems, you would have thought about the discrete Heisenberg-Weil operators, which are just the qudit versions of the Pauli operators. Qubit Pauli operators are two operators that commute, that always anti-commute when they're different. And now for qudit Heisenberg-Weil operators, the anti-commutation comes with a these root of unity. Yeah, and actually turns out that if you want to find a construction for these discrete Heisenberg-Weil operators, you can find them as a discrete subgroup of the continuous group of displacement operators. This is what this row here means. The whole point being that the set of continuous displacement operators form like a continuous embedding space for all of the discrete displacement operators. So all of your qubit or qudit quantum mechanics that you want to formulate, you can actually simply always embed into the continuous variant of these groups. Okay, so now it's a bit more of a math slide. Just to double down on what I was just saying, Lucy.
Is that in the previous page at the bottom? What kind of value does it take?
Sorry, where? Down here?
UV, yeah, yeah.
Oh, here. Okay, so what I mean by UV is simply takes a Pauli X clock. Oh, in this case it's integers mod d.
Yeah.
But in this case it's integers mod d. Yeah, if you want to embed it, right, like you might want to rescale by some factors. But that's really it. Okay, so we can think about representations of these discrete Heisenberg-Weil operators. And so now this is a little bit of fancy math that I adapted from this nice paper from Mumford. He gave Tata lectures on Theta at the Tata Institute in 1983. And one thing that I found really astonishing is that once you start to know a little bit about how the GKP code works, and then you open this paper, and like after 3 pages, you'll see, okay, hey, representation theory for Heisenberg groups, and then you notice, oh, okay, it's sort of the same thing. So in some very curious manner, Mumford has already sort of like written down the predecessor of the GKP codes back in that day. Okay, so what do we see on the slide? Okay, on this slide, I'm going to define two sets. One is simply the label set of displacements for Heisenberg-Weil operators. So on the previous page, we saw that, on the previous page, we saw that it has this label set of like integer mod d labels for generalized Pauli operators, and we have some extra phase. And basically, when you go to this page, this is exactly what's here. Okay, we have some phase index, and then we have integer labels, which capture, which give you a label set for powers of qudit Pauli X and Pauli Z operators, which label the discrete Heisenberg. So what's interesting in this paper is that you can construct holomorphic functions, you can define an action of this group on these functions, and then when you look for the irreducible representations of this action of the Heisenberg group, we find precisely that the irreducible representations are those are subspaces of functions that are stabilized by in a different label set where now I have like where I have now L times these indices as the basic labels. Yeah. So there's a lot of complicated language just to say that, okay, if you have a qudit Pauli operator, but the way that you define it, you can start by picking 2 displacements that have the right commutation relationship, and then you simply ask for these powers to define identity on whatever space that you care about. So this is a different way to think about the GKP code.
It's confusing.
Yes.
Seems like the mu had just a L. I mean, if I'm imagining how this page would go, it's a mu L, and I'll have Z mod L across Z mod L. But somehow there's L squared in the middle, the first thing, and then only L in the second one. What's going
Oh
on?
yeah, this is a weird convention.
But it
Rather,
makes
this-
sense.
it will make, yeah. I mean, this is a little bit confusion because this is a little bit confusing because it depends on how exactly you do this embedding. Whether in the embedding discrete label set into the continuous one, whether you do some rescaling or not. That's where this comes from. It also confused me a lot. So the point of this of showing these constructions is that is to think about GKP codes really as an embedding of the DV quantum mechanical system into a continuous variable quantum mechanical system. And it's nice that the thing that we'll come to think about as the GKP stabilizer group like explicitly shows up in building these irreducible representations. Okay. So yeah, and essentially, like we have these irreducible representations and we have this parameter L, then it's here. Then the dimension of the subspaces goes with L squared. This is and is spanned by Jacobi theta functions. This is not super important for what we're going to talk about. Okay, so this was a very, on the one hand, motivation for GKP codes coming from physics, and on the other side, the motivation for GKP codes coming from math. In practice, we rarely use this kind of language to think about GKP codes. All that we think about on a day-to-day basis is more simply displacement operators. Yeah, so I'm going to briefly talk about displacement operators. So we've seen them before. This is just a reformulation. So if we have an n-mode quantum system, continuous variable quantum system, then the phase space of that quantum system is 2n dimensional. We write down the corresponding generalized displacement operator that acts on all its modes at once by this dimensional thing there, which is an operator that takes this vector psi as an input, and it takes an arbitrary point in phase space and shifts it by psi. So if status x, you go to x plus psi. That's what the displacement operator does. In general terms, if you have two of these displacement operators, one with index sign and one with index eta, their commutation phase, or the phase up to which they fail to commute, goes with a symplectic inner product between these two vectors. So as we've seen earlier, I've already hinted at the fact that GKP codes have something to do with the set of displacement operators that commute, right? Then it is exactly this symplectic inner product that you want to be integer in order for the corresponding operators to commute. And then furthermore, if I take a state, or if I take a point in phase space and I shift it, I can shift it again, I can shift it again, and I can shift it again, where at the end, the total shift is simply going to be the sum of all the individual shifts. Yeah. So these are the commutation and the product rules for displacement operators. So now finally, what's happening for GKP codes is the way that I understand GKP codes is that GKP codes are simply stabilizer codes where all the stabilizers are generated by displacement operators. So you take displacement operators, you take 2n of these vectors. We have a 2n dimensional phase space, and so we want to roughly stabilize each of these dimensions in phase space. So you take 2n displacement operators, and you simply let them generate a group, because displacement operators never power to identity on the CB Hilbert space. This group will be infinite and discrete, therefore it will be isomorphic to a lattice. So this stabilizer group for GKP codes is isomorphic to some lattice, which is a Z span of these vectors that are put into the generators. And finally, importantly, to be a stabilizer group, we want the displacement operators to commute. Right? So we want this stabilizer group S to be abelian. What this means in terms of the lattice on the lattice is that the lattice that labels the stabilizer group needs to be what we call weakly symplectically self-dual. And so it needs to be contained in its own symplectic dual, where duality is defined relative to the inner product given by the symplectic matrix. So this is the question. No, I mean this.
Sorry, like
yes.
maybe I missed something. Like At this stage, when you talk about GKP code and stabilizer, like, is it obvious that it's going to provide some kind of error correcting property or?
Not yet.
Okay.
No,
So,
not.
so they're stabilizer in the sense of
They're
like,
just stabilized. They fix the subspace.
Okay.
That's it. So far, no error correction properties.
Okay.
Yes.
To satisfy all of these constraints, what does that impose on your choice of these vectors? Can they be arbitrary or?
So in principle, they can be arbitrary. There are two constraints that I point. I said we need two n-linear independent operators.
Yeah.
Sorry, or vectors, right? Because in order to go into cover every direction of phase space, this is one condition. The other condition is that these vectors are such that the lattice spanned by them is weakly symplectically subdued.
No.
Right. And that's just one-to-one with the fact that stabilizer commute. Right. And these are the two conditions that we care about. With the rest, that's it. Right. Like that's all we care about.
So does this mean that phase is zero? That multiply?
Yeah.
That's it.
That's it.
Okay.
That's it. Right. Yeah. So these are three different formulations for just saying that these stupid phases are zero. That's it.
The language of physicists, this basically means you want a crystal lattice that is polar reciprocal lattices itself.
Relative to the symplectic inner product, but yes.
Okay.
Yeah. I mean, if you think in terms of solid state physics,
Yeah.
right, then reciprocity or dualness you usually define by the Euclidean inner product, right?
Yeah.
Like coming from like Euclidean Fourier theory. You can, yeah. I mean, here we simply work with the symplectic inner product, which is motivated by the symplectic structure of phase space. But that's the only difference.
In quantum Hall, if you had a magnetic field, then you have these magnetic translations, and there's certain lattices where they can have those can be vectored. These are those.
Yeah, I'm actually going to talk about it. Okay, so why is this framework meaningful? Well, we simply wrote down the code where the stabilizer group is displacement operators. Yeah. The stabilizer group being displacement operators and us only thinking about displacement operators is going to lead us to also find that the operators that behave like logical Pauli operators, they're going to be roots of these stabilizer displacement operators. They are also displacement operators. So everything is displacement operators. So if we are given an arbitrary other quantum error correcting code, say the toric code or something, some LDPC code that you might want to think about, you can simply take that code, replace every qubit in that code by a mode of quantum harmonic oscillator, and when you write down the stabilizer group for the code that you care about, you simply replace every Pauli operator by a logical Pauli operator displacement of a single mode GKP code. Yeah. So what that's going to give you, like that's going to give you a GKP concatenated qubit or qudit error correcting code. But now everything's displacement operators. So you can take any arbitrary qubit or qudit stabilizer code and turn it into a GKP code in the sense that GKP codes are simply codes which are given by displacement operator. So in the same way that you embed the discrete Heisenberg-Weil group into the continuous one, you can also take arbitrary codes with larger stabilizer groups given by discrete Heisenberg-Weil operators and embed them into the continuous version of those as given by the displacement operators. Yeah. So this is the point that I want to make here, that you can really use the framework of GKP codes to think about every stabilizer quantum error correcting code as a GKP code, which makes this a relatively powerful and general framework, and it helps that we get to think about lattices, which are inherently geometric objects, and sometimes a little bit easier to think about than all the nitty-gritty combinatorics that you have to do for qubit systems. Okay. So this was a lot of yes, I have a question.
So, sorry, can every lattice code be constructed this way?
Sorry?
Can every code define a lattice?
So every GKP code defines a lattice. Not every lattice
Can be constructed by this code concatenation.
Not every lattice is necessarily a GKP code.
Yes,
Right,
but
like-
for the ones that are, like, can you always use this kind of intuition from qudit code?
Oh, sorry. So your question is whether every lattice is corresponds to a concatenated code.
Yes,
No.
that is a code.
No, not every lattice corresponds to a concatenated. Like the concatenation is a pretty strong structure.
Right.
That it tells you that, for instance, for the lattice, you like a concatenated code has the qubit stabilizers in there, And then you have all the stabilizers that turn the modes into qubits or qudits, right? And so you have this like trivial substructure in the lattice that is represent, and this trivial substructure doesn't necessarily exist in every lattice, as far as I know. Like if you're more familiar with like lattice theory lingo, but you would think about qubit concatenated GKP code as so-called construction A lattices. I'm not sure whether anybody's familiar with this. So this is like Conway Sloan language in their yellow book. Yeah, and if you Google this, like you'll find okay that there's some more stringent conditions on orthogonality and so on. Yes, Lucy.
I understand this concatenation thing. I mean, and how it gives you this? How many layers of concatenation are you thinking about?
Well, on this slide, I was just thinking about one. Right? I take I'm like, I have a qubit quantum arithmetic code, and I replace every qubit with a GKP encoded qubit. That's it.
Okay.
Right.
I think concatenated with the GKP.
Yeah, with a single mode GKP that turns the discrete Heisenberg-Wall operators into displacement operators. Simply, that's.
Yeah, I thought it was concatenated with itself.
Oh no, yeah, I don't know how that works. I mean, yeah, I mean for GKP codes there are weird constructs. You can take products of lattices and you can do funny things, but yeah, but concatenation is a bit ugly to like try to concatenate GKPs into itself. It's a bit, yeah.
Can you get a GKP code out of it after I concatenate?
If I concatenate GKP code into qubit code, I always get GKP code simply because the definition is so broad. Right? Like the definition just says, okay, hey, GKP code is whatever stabilizer code is made up of displacement operators. And you can simply view every stabilizer code as being made up of displacement operators. That's a point. Okay, so we're now going to focus in a little bit on a simple example. See, okay, it should be right. So the most simple way to construct a GKP code, which was also already featured in the original paper by Gottesman-Kitaev-Preskill, is what I call the scale GKP codes. And the idea in scale GKP codes is simply we build a lattice by starting with a symplectically self-dual lattice. So how do you do this? We start with a symplectic matrix. Symplectic matrix is one that satisfies M0 that satisfies this condition, and the rows of these symplectic lattices span a symplectic lattice. So you can start with a symplectic self-dual lattice like Z2, right? Like just a normal square grid on a plane. And this lattice, since it's symplectically self-dual, has the fact that all of the, so now if you unpack this relationship, you find that all of the corresponding displacement operators commute. So the commutation phase is always an integer. In this case, it's either 1 or 0. So now, when you rescale this, we take an integer, we take the square root of an integer, and then we take the lattice and we blow it up with this square root of an integer parameter. So what this does to the commutation phases is the commutation phase is simply going to be scaled by an integer. But integer times an integer stays an integer, so the stabilizers stay commuting. Okay, what happens in the picture? In the picture, I'm drawing two lattices. So we have or GKP, this is a stolen picture. Gottesman, two lattices. In this picture, what happens is you start with a Z2, so unit volume square lattice, and you multiply it by a square root of 2. So what's happening is that the stabilizer, the lattice corresponding to the stabilizer elements simply becomes bigger, right? Like so the unit cell volume now move from 1 to 2. But at the same time, now you've made space for its symplectic dual. Okay. And so symplectic dual was a lattice given by a set of points that have an integer inner product with all of the points in this lattice. So now if you have take 1 and I scale 1 to square root of 2, then now suddenly I get these numbers 1 over square root of 2 that I can multiply to square root of 2 that give me an integer again. Yeah. So as we scale up the stabilizer lattice, we now get a symplectic dual lattice that is scaled down, but that has a more finite grid. So in the language that we provided, the coarser lattice corresponding to the lines in this picture corresponds to the stabilizer group of the like of the scaled GKP code that we constructed starting from a symplectic lattice and its own symplectic dual corresponding to all the operators that commute with all the elements in the stabilizer group is now scaled down. Okay, so, and these operators are precisely the logical Pauli operators of the GKP code. So another way to read this picture is our scaling factor over square root of 2, is that the dotted lines, the lattice given by the dotted lines, presents the lattice of logical Pauli operators. The fact that the unit volume, that the volume spanned between one of these logical operators and stabilizer operators always in integer means that these are operators that commute. It's even integer means that these commute, and that's the convention thing. And then here, the volume between the logical operator and another logical operator is one, which corresponds to its computation. And you need two logical operators. So if I apply a logical operator twice, like Pauli x squared, I get back to the stabilizer as a logically trivial action onto the code space. So this is how to understand this. This is how to understand this picture. Okay, so we have a phase-based formulation for the logical operators and the stabilizers of the GKP code. And understanding the logicals now also gives us a way to define distance for the GKP codes, which in this case is simply defined by the shortest vector of the corresponding lattice. So the distance here is the shortest norm of logical operators at another stabilizer, which corresponds up to the scaling factor exactly to the shortest vector length of the symplectic lattice that we started out with.
And this so happens to be the code distance, right?
That's one-to-one to the, I mean, yeah, code distance as defined via the Euclidean norm.
Yeah, I just wanted, because that's not necessarily integer, right? That's square root.
Oh yeah, sorry. Yeah, no, this is exactly, yes, but I mean, that's it. Like here we think about Euclidean distances because we're in phase space and the error model considerations are guided by something continuous. Right? So you think about like displacement errors and so on, right? Rather than Hamming distance, where you like which is what you think about when you have like a discrete error model where bits are flipping or not. Okay, so this was a simple example of a one-mode GKP code. This is a square. The previous slide showed you the square GKP code that everybody knows, but the constructions that it provided is very general. Right? Like all that we did was we started with a symplectic matrix. We looked at the lattice it spans, and we multiplied that by some factor that gave us a GKP code. So we can take this step and we can think about the scheme and simply zoom one step out and ask, okay, but now what is the space of all the possible GKP codes that we can think of? Yeah, and so in order for this, we need a little bit more algebraic tools. So we're gonna write down the generator matrix for the GKP code, which is simply this matrix on which the rows denote the lattice basis vectors for the lattice that we think about. And the lattice itself, since it's the integer span of these rows, is invariant under some reparametrization of these integers. Yeah? So what this means is that you can perform a basis transformation, which is a left multiplication by unimodular transformation. It's going to change the matrix, but it's going to leave the lattice as a geometric object, as a z-span of that matrix invariant. Yeah. So when you want to quantify the space of all possible GKP codes, that's actually simply given by all the possible symplectic matrices modulo all the possible basis transformations. So this is the arithmetic way to capture the whole set of GKP codes that are constructed via the scaling construction that I just showed before. Okay, and so the space Yn, which is exactly this quotient group, this is a set of geometric objects. Like, so these are matrices, modulo basis transformations, and then each element in this in the quotient group that we've constructed this way is one-to-one with a label of lattice, which is a purely geometric thing. Okay, so we have to dive a little bit more deeply into some algebra that capture this. For simplicity, but I'm not going to talk about the general n-mode case so much, but I'm going to focus on the single-mode GKP codes. The theory turned out to be complicated enough. And if you want something more complicated, you should ask Ansgar, who is visiting here and who's thinking about the N mode. So it's in the back. He's thinking about the N mode case of GKP codes very much. Okay, so I'm going to give you a reformulation of the lattices, simply to understand better what's going on and how to think about GKP codes in these geometric terms. So for the single mode GKP code, right, like we have that the single mode GKP codes are given by the, you can construct them by the space, like as elements of the space of all possible lattices in 2 dimensions. Since we're now in 2 dimensions, we can either think about the lattice as embedded in some real space, R squared in the real plane, or because we're fancy, we can think about it as a lattice embedded in complex space. Like, complex space formulation is nice because if we now go to this complex plane up to an orientation and a scaling factor, which you can always adapt, you can parameterize the whole lattice and become one single complex number. So we fix one of the basis vectors to be 1, and the other basis vector is some complex number where the imaginary part is non-zero. And without loss of generality, we simply fix this second complex number tau to be in the upper half plane. So we have this like one index in the upper half plane that fully captures the whole structure of the lattice. What do basis transformations do to this reparameterization? Well, if you took this lattice and you change the basis and then you go back to like some standard form that has this tau parameter, then what you find is that the basis transformation implemented by multiplication of the generated matrix with this matrix here just implements a Möbius transformation of this tau parameter. And so this is just the action that you find. It's a fancy reformulation, but it's nice because it allows you to understand the whole space of possible GKP codes as now the upper half plane modulo the action implemented by any potential basis transformation. Yeah. So we can think about this. For instance, if we choose the matrix 1, 1, 0, 1 here, what this does in terms of space, in terms of this Möbius transformation, is that it takes a point here and you choose a point here. Yeah. So by modding out this Möbius transformation action, you're actually taking the whole upper half plane and you're modding out everything into these fundamental cells, which are infinite triangles. The upper point of this triangle is that imaginary infinity, and you have this structure here. Yeah, so this is upper half plane picture of the space of all possible GKP codes. Lucy, you have a question? Yeah.
What is when you do this going to complexify it? At the end, do you look back at real stuff again because the original was real? Like, and you can show us later, I guess. Like later.
I mean, I just
complex.
I'm just gonna stick with complex now, actually.
But isn't the original problem about real?
Oh yeah, I mean, if you want, you can always go back to real, but since the complex notation is more compact, simply it allows like it's. And
You added dimensions, did you know?
No, I didn't.
Oh, if you complexify just one dimension or one real dimension, one, and then the imaginary dimension is the other, or
yeah.
Okay.
Yeah, that's it. But like it's xy maps to x plus iy.
Yeah.
That's it.
Okay, I see.
That's it.
And then the other question is, like you mentioned that not all lattices are corresponding codes. Like, have we seen, like, is it clear where the missing lattices?
Oh, okay. So I think there was a previous question. So what we wanted was to correspond the lattices that we care about here with stabilizer code, right? So it's corresponding. The displacement operator should commute. So the condition for
code.
Sorry.
So they come from stabilizer code.
We want these lattices to be stabilizer codes. So the lattices that are not codes in this formulation, right? Like are those which are simply not weakly symplectically acceptable. So they're not contained in their own dual.
So by restriction to SP, they already picked out the one that corresponds.
Yeah. In like within SP, we already like natively built this in.
Okay, great.
Right? We don't need to narrow down.
20 minutes since we started.
Thanks, sorry.
Sorry?
You have about 20 minutes since we started.
Okay, cool, nice, thank you. Okay, because now the fun stuff starts. Okay, okay. So we've talked a lot about lattices. Lattices are still, like these discrete infinite objects, which are a little bit cumbersome to handle. So a different way to think about these codes is, rather than to think about lattices, is we can think about tori. Right? And the way that this works is that like our lattice was a lattice in the 2-dimensional phase space can actually also just take this two-dimensional phase space and mod out the lattice. But like when you go from, I don't know, like some band structure to a Brillouin zone, you mod out the lattice. What you obtain is a torus whose first homology group over Z reproduces the lattice exactly. Yeah. So thinking about the torus is nice, because now at the end of the day, when you start to think about gates, right, like when you implement, say, a Hadamard gate for the GKP code, what that does is it takes a lattice and rotates it by, say, pi over 2 or something like this. Right? Like, so logical Clifford gates for GKP code, as we will talk about a little bit more later, are given by lattice automorphisms. Right, like so, and implemented by Gaussian unitary transformations. In the torus picture, those are again just automorphisms of the torus, right? Like, so you take a torus, you do some Dehn twist, you squiggle it and move it back to itself, and that thing, like, is exactly the kind of operation that implements the Clifford gate. So, in fact, this whole project came about when I was trying to think about how to generate automorphisms of or how to generate Clifford gates for the GKP code. And if you play around with it a little bit, you'll figure out that the generating set is given by the vector representation of Dehn twists, for those who know what that is. Right? And that builds a natural bridge to this more geometric, more topological formulation for.
What is that Dehn twist, you know, or you also need, so you need both S and T.
You can build everything using Dehn twists, right? Like the symplectic transvections, which represent Dehn twists, they form a complete basis for the operations. Yeah, I mean you can use S and T, but you can also like use T and T transpose, sure. Right? Like or other things. Right. Okay. So that's a funny stuff. But now we still want to narrow down our language a little bit more to the GKP code. So now for GKP code, we have we may want to use one extra piece of information. So here in this picture, I've drawn a point on the torus. What does this point mean? Well, this point, if it lives on the torus, it's a point in the complex space that doesn't know about the homology of so like there's no information in this point, which just is on the torus, is whether this one corresponds to a loop or not. So this is the point in the space that doesn't know any logical explanation. That's why we use the GKP code. In other words, you can put a point on this torus and can use it to represent a syndrome of the corresponding code. Yeah. Yeah. Another way to think about it is right, like this. This is a whole like labels set for points in phase space. And if you take a point in phase space, right, take a GKP code, you displace it a little bit, but then you mod out the logical action. Right, what you're going to get is a displacement modulo logical action, and that's precisely the formulation of a syndrome. Yeah. So we have a torus whose homology group now labels the logical elements of corresponding GKP code, so that Dehn twists or other topological moves that braid these things around, but preserves the total intersection number, implement Clifford gates. And if we consider points on this torus, those are essentially labels for the syndromes of the corresponding GKP code.
There's a question in the chat. Complex tori are not necessarily biholomorphic, but all the underlying real tori are diffeomorphic to the standard torus. The original problem we have was formulated in real phase space.
Right.
So shouldn't we work in complex phase space to begin with to get a richer class of possible GKP codes?
I don't know the answer to this question. I've never thought about this, so I don't know.
We have a C there.
We do have
kind of in complex phase space already.
I don't know. I've never thought. I don't know what a complex phase space is. To be honest, but
I was thinking he meant
like line
R2 versus C. Like,
oh yeah, I mean you can do that. Yeah, I mean you can totally start with a like in Segal-Bachmann representation for quantum mechanics. Also, you start with like space labeled by complex numbers, and all your states are holomorphic functions. You can do this.
So each mode is like one dimension. I thought they meant each mode is one dimension.
One complex dimension.
Yeah.
Yeah.
So like
no, that makes sense. Yeah, you could do
should
that.
be equivalent.
I thought that
my guess.
I thought that this was equivalent, but then they said something.
But in the case of spherical codes, you get more stuff if you look at complex polytopes. So I don't know. Like,
Oh, because you have some Galois symmetries or what?
I don't know, just there's more stuff formulated in complex things that are defined as polytopes in the complex space. But the definition of lattices in complex space and lattices in real space seem similar, so I thought they would be
Yeah,
equivalent, but I don't know.
that's what I thought. I mean, the behavior of functions on these spaces and how to map to another, right? Like if you think about complex spaces, you always want to think about holomorphic functions, which are a stronger restriction than just thinking about continuous functions on real spaces.
Maybe
So-
at the end, we can have them go on the microphone. And discuss.
Yeah, would be
The
Like,
journal
would
stuff.
be like, yeah, exactly. It would be nice to clarify what this means. Yeah. Yeah, I mean, you need more for holomorphic functions than just for real functions, like continuous real functions, which might be where this question is stemming from. But I'm generally not sure. It would be nice to clarify. Okay, but yeah, let me just mind my time. Oh my God. Okay, so where's this construction, right? Like where we have a torus, we have a complex torus, where the homology elements or the structure of the torus is coming from the lattice that has been modeled out, gives you the structure of the code. And if you have points on the torus, that labels the syndrome. Right? So this pair of a complex torus together with a point on this torus, if you open a book on elliptic curves, people will tell you, oh, this is an elliptic curve. This is one way to represent a complex elliptic curve. So we wanted to dive into this a little bit deeper. So there's again some math. This looks more complicated than it really is. So maybe we start at the bottom right corner. So those of you who know elliptic curves from crypto, you know that elliptic curves are solution sets to polynomial equations, right? Like y squared equals x cubed plus some stuff. In crypto, you usually do this over some rational numbers or some other number fields. In our case, since everything's formulated over complex numbers, we also think about these polynomial equations as over complex numbers, where everything becomes really, really nice. And so it simply turns out that you can take this elliptic equation with these two parameters, and it can be solved by some function that's called the Weierstrass theta function, which has a periodicity up to lattice transformations. So this is the function on the torus that solves, that solves this elliptic curve equation. That this point builds a bridge between the torus and the elliptic curve equation, and it actually turns out that these two parameters that go into the equation, they're called the Eisenstein series. These are two complex parameters which are a function of the lattice. So you take lattice points, you sum them all up, raised to some power, that gives you these constants that depend on the lattice. And it turns out that these two constants like fully fix the lattice. So these are now, but now we've gone from thinking about a lattice as something, like with two real vectors spanned to something that to an element that's spanned by one complex vector in the arxiv plane. And now doing the third formulation where we can think about a lattice as being fully parameterized by two complex numbers, which go to this elliptic curve equation, whose solution tells you something about the torus. So it's a ton of correspondences, but this way to formulate it, the lattice is nice because we can use the properties of the equation to do something interesting. Yeah. So now that we start to work on over the complex number fields, right, we know that polynomials factorize over the complex numbers. So we can take this equation, we can write it into its roots. Yeah, so now E1, E2, E3 are exactly this function here evaluated at half of one lattice constant, half of the other lattice constant, and half of their combination. These three complex points form exactly the roots of the complex equation there. For GKP codes, we wanted in the first place that the lattice is non-degenerate. Yeah, so what this means is that we actually have a lattice that spans all of phase space, and none of the lattice vectors is shrunken down to zero, essentially. Yeah. So this equation now gives us a way to interpret this. Right? Like if one of these lattice vectors became linearly equivalent to one of the other, or was shrunken down to zero, this would correspond to a matching up of these roots. So non-degenerate lattice maps one-to-one a degenerate lattice one-to-one maps to the degeneracy of this polynomial equation. So degeneracy just meaning whether or not they're distinct roots or not. Yeah. So this kind of structure is captured by the thing called the discriminant, which is really just I take the roots, I square, like I build the difference, I square that to sum it up. And essentially what this function, the delta function here tells you, if it's 0, then there are double roots in this polynomial equation. If there are double roots in this polynomial equation, as I've just argued, the lattice is degenerate. That means there will be one lattice vector that essentially is 0, which means the distance is 0. Yeah. So there are a couple of steps here, but yeah, but it's still a funky construction. Okay, a different way to write this discriminant function on whether or not roots are 0 is in terms of these constants G2 and G3, and the function that captures this is exactly G2 cubed minus some constant times G3 squared. Yeah, so this is the discriminant modular function that captures the degeneracy of the lattice. So now back to the example, the lattice is singular, like singular meaning degenerate, meaning that the distance of the GKP code is 0 if this discriminant modular function is 0. So if we go back to the previous parameterization that we had as one of these complex parameters, you can think of the following example. Example is a square lattice, and we squeeze it. Right? Like if we keep squeezing a square lattice more and more and more, since this thing has to maintain the volume of 1, one of the vectors is going to go infinitely large in the limit, and one of the vectors is going to go infinitely small in the limit. But the distance of the GKP code was the length of the shortest vector. So as one of these vectors gets infinitely short, the distance of those corresponding GKP codes approaches 0 in this limit. And it's exactly this limit where this discriminant modular function becomes 0. So these are a couple of different ways to understand the same picture. It's the same feature. Okay. So now we finally come to understand the pictures that we started out with. One thing that I didn't tell you is that there's some redundancy in the definition of these functions that allow us to simply rescale them without changing the lattice that we're labeling to be normalized. Oh, and this should be square here, not a cube. To be normalized. So now when we take these two conditions together, we simply take these two complex numbers, we normalize them. This gives us, this was two complex numbers, so we have a 4-dimensional space. We normalize them, we go to the 3-sphere. But now we want to exclude all of the lattices that have a distance 0, corresponding to the distance 0 GKP codes, which means that we take the 3-sphere and we cut out whatever the solution is to this equation. And so it turns out that the solution set of this equation within the 3-sphere is the trefoil module. So this is the explanation of the picture that we started out with. The space of all GKP codes is given by the 3-sphere minus the knot complement. And the idea, so now this is the space of all possible codes, that's the space of all possible, like all relevant lattices. And the idea now is that as you try to implement the Clifford gate, right, by applying a Gaussian unitary transformation, you're going to deform the lattice in the smoothest manner. And what that means is that you simply switch from one lattice to another, you switch from one code to another, and as you implement the logical Clifford gate, you're going to do a loop in the space. You're going to go back to the same code space that you started out with. But now, potentially, you're going to have wound around the topological defect in the space of lattices in a natural manner. So this idea gives fault-tolerance a topological origin and connects to what we see in dynamic in terms of fault-tolerance.
You also have the logical dimension you have to put in there, right?
What do you mean by logical dimension? Oh, sorry. Yes. Yeah, the construction is, but this is more simplified than the actual construction. Like
logical dimension 1.
That's right. Yes.
And it really, at each point, you have like a space.
Yeah. So yeah, things that I talked about Clifford gates, and you want for Clifford gates on qubits, you want the property that Hadamard squared is identity or something like this, right? Like, so there's some modulo stuff that you have to think about. This here is really just on the space of lattices. the kind of structures that you really want to think about that build a better translation to GKP codes are called elliptic curves with level structure. Where this level structure captures the dimension. It's a bit more, there's some extra parameters.
So it's not that like you have a space at each point, this S3 minus trefoil, and you're just moving.
Yeah, exactly.
It's not like.
It's not exactly that, but it's close. I mean, but this point still holds, right? There's homotopy. The mapping of the homotopical passes is still one-to-one with the ones that you would obtain. It's not one-to-one, but it's like still holds in the same manner. Or the ones with level D structure where you also have a logical dimension, only then you have some extra modulo stuff. Yeah, this is in the paper. I think it's too complicated. Okay, now a very funny thing of, these these functions that you think about are functions of geometric objects. Yeah? And there's a very famous class of functions of geometric objects, which are called modular forms. And you can use techniques from this toolbox to actually show that if the distance of the GKP code is bounded by lower bounded by some constant, then you're also a bounded amount away from this topological defect in the space of all lattices. So this is just to ensure that if you want your fault-tolerance to mean that I go through a sequence of codes, I never go into a distance 0 location. This means that if you do this, then you'll also stay away from this defect and you generally wind around if you go back to the same spot. So in the last way to look at this, right? Earlier I showed you these three roots of the elliptic curve that now live on this curve as these red points. As you implement the logical Clifford gate, what actually happens, right, is that you take this unit cell of the lattice and you're deforming it back to itself. So what's funny is that as you deform this, you can think about taking these 3 points, that's down here, and simply applying a shear of the whole lattice. And as this happens continuously, and these points are never allowed to go into each other, if the lattice distance is supposed to stay non-zero, and they're effectively going to break around one another. So this is maybe a little bit more to digest. The whole point is that you can use this way to derive that the homotopy group of the space of all possible GKP codes is exactly the break group on 3 strands. Right? And as you implement a logical Clifford gate, you realize one of these braids.
But the representations are not such that you get universal gates.
No, this is all. Yeah, this is unfortunately not in this formulation. Maybe there's something, but yeah, I think there's a lot to extend. Okay, so now we get to the final 2 slides. Sorry, I hope
4 minutes.
4 minutes. Thanks for checking. So this kind of formulation brings us finally to the idea of Gottesman and Zhang and Lucy in a nice paper that they put out in 2013, where they proposed a formulation of fault-tolerance based on properties of the Grassmannian of a Hilbert space. And the idea is, ask Lucy, ask Daniel, ask Ansgar if you want to talk more about this. The very rough sketch of the idea is that you want, instead of thinking about individual codes and individual errors and the ad hoc representations of the codes, you can simply think of the space of all possible finite dimensional subspaces of a given physical Hilbert space. Yeah, the set of all these subspaces of a physical Hilbert space is what's called the Grassmannian. And if you think about error-correcting codes as simply being points on this Grassmannian, right, like a code space is one of the subspaces of a physical Hilbert space. If you realize the unitary gate, right, you're going to go from one code space to another code space to another code space until you return back to itself. And the idea was to realize fault-tolerance, or find a sensible definition for fault-tolerance, in the sense that if you want to implement logical action in a fault-tolerant manner, that has to correspond to a homotopically non-trivial loop in this Grassmannian space. So this is and as we've just demonstrated, that if you go through a sequence of GKP codes as captured by these lattices, then you realize exactly that. Right? Like then you're exactly realizing a homotopically non-trivial loop that closes and implements a homotopically non-trivial link with the trefoil that captures the zero distance code defect subspace of GKP codes. Okay, so that's a connection. I hope you have a rough understanding of the picture that we started out with. I think this whole theory is pretty rich, and there's a lot to explore. So one of their motivations, or one motivation as a physicist that I can see for this construction, comes from what people call holonomic quantum computation, where some Hamiltonian, you have with some parameters that adiabatically vary until you go back to themselves, and you want to implement gates via holonomies, like via barrier phases or via other non-trivial operations that happen on the states as you traverse some closed loop. Right? So the same kind of, like one of these examples will be, for instance, Aharonov-Bohm phases as you like wind around some flux tube or some electrons on a plane. So yeah, so the whole story that I've been telling, that I've been trying to convey, is that GKP codes, or by thinking about GKP codes as they have such a nice and sort of like easy to think about connection to lattices, is that they really give you a way to build a dictionary, build a bridge between thinking about coding theory, thinking about fault-tolerance, and that this bridge is being implemented, right? Or like, yeah, I mean, coding theory as captured by surfaces and tori and geometric objects. That this connects to the ideas of fault-tolerance through an understanding of the symmetries of the corresponding codes. Yeah. And this is nice because general, as I've tried to argue, GKP codes help to embed all possible codes. So there's hope that you can use the kind of structures that we've been looking at to also look at like to embed other qubit quantum arithmetic codes, try to understand their properties, and try to see if we can use the same framework to have a geometric understanding of properties. Like this is something that Ansgar is actively working on. Yeah, we should talk to him. He's still going to be until November. So, okay, finally, in the very beginning, if I get a single minute, I've also promised a bridge to physics. So in the original paper by Gottesman-Kitaev-Preskill, they also already pointed out that you can realize it's a physical state representing the GKP code by putting an electron on a torus that has a perpendicular magnetic field acting on it. So this is one of the prime examples of a quantum Hall effect system, where the electron wants to move on the torus, but it's being forced into some clockwise motions. And it essentially, like, I don't know, in my mind, I'm thinking of the electrons like Pauli repulsing itself. So that like the effective state that lives on the torus starts to become grid-like within the boundaries of the torus. So this was realized by Gottesman-Kitaev-Preskill and Ganesh and Levin and Rimatz, DiVincenzo et al. Also had a paper where they realized that you can build an understanding of the GKP code as the ground space of a quantum Hall system for a qubit at filling fraction Newton's 1/2. Filling fraction here just means how many flux tubes pair with electrons. Or if you want qudits, then it's simply 1/d. Yeah. So you obtain this kind of map by you take a GKP code, you write down it's Hamiltonian, but like it's stabilizer Hamiltonian. You can do a couple of mappings. I'm sorry, you go the other way around. If you write down one of these quantum Hall systems, you project into lowest Standard level, or if you start with a torus, you'll realize that you effectively simply get out the GKP stabilizer Hamiltonian. And if you write it into this Zag basis, which is a natural way to formulate functions on a torus, you get out exactly the structure where you have a torus with some periodic potential that lives on this torus, and then you get magnetic moments happening on the torus and tell you about the movement of this particle relative to this. And now the interesting thing is that I've generalized this formula from their papers to n dimensions for arbitrary GKP codes. And it turns out that you can take an arbitrary GKP code, and as I've mentioned earlier, this embeds all possible stabilizer quantum arithmetic codes. You can simply realize arbitrary GKP codes as one of these quantum Hall-like systems, where now the properties of the code, how exactly different vectors or different stabilizers relate to attributes of this code and information about the distance are essentially captured in a correlation between the magnetic momenta of this kind of system. So this sort of builds. So here, this is just yet another fun example on how learning about the GKP code allows you to take a coding theoretic object, the GKP code, and embed it into a physical system.
Did you do this in the Rosetta Stone paper?
No, this is my thesis. This is not in the paper. Right. Okay. So, right. So, yeah. So there's lots of things that I've talked about in this talk, and I'm gonna come to an end. Yes.
So when you look at the deformed GKP codes, not just the square, how do the wave function of these electrons look like? They still
I haven't plotted them. I don't know. I mean, in the Hamiltonian, but like that's simply gonna be a change of these S's. The wave function for the hexagonal GKP code, in terms, I mean, if you look at the Wigner function really just looks like a hexagon. It really just looks like a deformation of the square GKP code. Wigner function.
The same Jacobi.
It's a similar kind of, it's the same kind of structure. You can just realize it by changing the tau. In the
Okay, so it's just the change of tau.
It's change of tau. It's a change of tau. Right. And as you already pointed to it, but like there's some nice work in the literature on what people call Hall viscosity. Right? And so what's happening in this realm is, you put electrons on a torus with a magnetic field, but now instead of changing the magnetic field or perturbing otherwise, you twist the torus, right? You apply some automorphism to the torus. And what's going to happen in this case is that the electrons on the surface of this torus are going to start moving around back to their own initial position. But since there was a perpendicular magnetic field piercing the surface of the torus, these electrons may or may not have like effectively wound around one of these flux tubes that exist there, leading to a barrel-like phase. So the last comparison that I'm trying to make is that this picture of taking the single mode GKP torus in the complex plane that we just looked at, we perturb it, and wind around the defect in the space of our lattices. I conjecture that you should be able to build a correspondence between that and the barrier phases that you accumulate in a Hall viscosity type of situation. Yes.
So now this equation that you wrote, so quantum Hall systems are chiral, and usually quantum correcting codes are non-chiral.
Yeah. Here I'm just I mean this is the thing that's addressed in the Ganeshan 11 paper. In my case, or in the formula that I just wrote, I'm just looking at the book. I'm looking at the most simple properties. So.
Yeah, but for instance, there on the right-hand side, you have a pair number, a bunch of variant complex the GKP.
I don't know. That's a good question. I've been trying to find out. I mean that's the thing that I really like, right? Because there's this correspondence between quantum Hall and GKP. Want to understand, okay, what is the coding theoretic equivalent to the quantized conductance, right? Like, or other TKN invariants. Yeah. I think this is a really interesting question. There's some needs, right? But I don't have a clear answer. Sorry, some other.
Yeah, some other.
Yeah,
it's all related to the SLT matrices of the quantum Hall sequence. Yeah.
Yes. Yeah. No, I think this is we should chat more. I think this is a great question. And finally, I mean, this is an idea that I'm discussing with Victor, and I'm going to wrap up. So I think you can also think about displacement operators as like a simple case of vertex operators that you find in other realms of physics, and maybe understanding this will help you to generalize. So I'm going to close this talk now. The whole gist to take away is, GKP, it started so innocent, but it's something that people now build in the lab. And as I've showed you today, like we have this like relatively innocent quantum error correcting code, which actually connects to relatively non-trivial ideas in algebraic geometry and more fancy math, which I think is really exciting that like through coding theory, we have like a tabletop bridge, and not string theory, but tabletop experiments bridge between physics and very exciting and fancy mathematics. So that's the main gist that I hope that you can take away from this talk. I thank you all for your attention, and my collaborators, Ansgar, who's here. He gives very good talks, you should make him speak. and Steve, who I couldn't find. yeah, so our paper is on the archive, also accessible under this QR code. And if all goes well, we'll have 2 more papers that come out very soon on related ideas. Yeah, so that's all. Dr. Ansgar, and thank you all for your attention.
Just today there was a paper out realizing that Yale GKP qudits, qtrit and qcore encodings beyond the break-even regime. Very timely. Yeah, and like superconducting circuits, microwave cavities. Product.